Well, hello everybody. This is Dave, and today we're going to wrap up our discussions about a two-sample significance test with this idea of comparing two means. There is going to be a lot of discussion that's similar to the lesson on two proportions, so I'll try my best to get through it rather quickly. Much like two proportions, again, if we're dealing with two means, we're dealing with two separate populations. This is different than paired data. So it's important to keep your information organized according to subscripts and recognizing, again, of course, when you're given population parameters and when you're not. So you can see at the bottom, we've organized things according to subscripts 1 and 2. So let's take a look at an example problem here. And here we have a survey dealing with the heights of 10-year-old girls versus the heights of 10-year-old boys. Well, these are two different populations, of course, and when we take an SRS of 12 girls and 8 boys, now we will have a sample of each of the populations, which means we're going to be dealing with this two-mean significance testing scenario. If we want to do the difference, again, we just have to remember that the difference may be negative if in this case, the average of boys' heights is higher than the average of girls' heights. So if we do the exact same thought process that we did with proportions, if we take a look at the first population and we simulate that out, we take a look at the second population and we simulate that out, and then we do a difference of these particular means and take a look at that distribution, we can see what we've seen in the past. That if we're talking about the shape of these distributions, the sampling distributions are all normal. If we take a look at the center, we can see that the center of the difference of means sampling distribution is actually the difference of the two means in the previous population distributions. When we look at the standard deviations, they don't look like they do anything yet, but of course we know from previous experience that when you combine standard deviations, you actually have to turn them into variances first. So take that standard deviation, square it, and then you can add them up. The difference between dealing with differences and dealing with differences of variances is you still add up the variances no matter what. So if we talk about the summarization of what these distributions look like, we can see that again the shape is going to be normal. We will have the situations, of course, that if the sample size is not large enough, we're going to have to deal with the conditions to prove that we can still use the normal distribution. Remember that we're dealing with means, which means the CLT is always a potential. If we're talking about the center of the sampling distribution of the combined populations, well, we know that that should be representative of the parameters of interest, which in our case is mu1 minus u2. If we take a look at the spread, again, looking at the equation for the combination of variances, to find the standard deviation, we would have to square root both sides, and that's where we get this particular equation for the standard deviation. Of course, with all scenarios, in the case of sampling, because we're sampling, the 10% condition must be satisfied. So here's a look at the picture of this distribution, and just like proportions, we can see that the center should be the mu1 minus mu2. The standard deviation is what we said would be calculated, and the sampling distribution, of course, deals with the differences of these sample means of mean 1 minus mean 2. So we can summarize these ideas on the following slide. Again, the first thing we would do is talk about our difference between the parameters of interest. As long as the 10% condition is met, we could actually find the sampling distribution's standard deviation using the equation given. But the thing that we have to watch out for now is when we start applying these into our calculated situations, we may end up in a t distribution scenario. So again, this would be the equation if we knew the standard deviations of the population, but as we know, in most cases, that's not going to be true. When that's not true, we're going to go ahead and we are going to estimate the standard deviation with the sample standard deviations. And so in this case, the standard error for this statistic will become s sub 1 squared over n1 plus s sub 2 squared over n2. So big difference there. And again, you have to read into the problems and find out, do we have this information or not? Don't just start making up numbers. If it's not stated and there's no way to calculate it, then you have to estimate using these sample standard deviations. That means that if we're going to calculate the t-score or the test statistic, we're going to calculate it very much the same way we've done in the past. where we have our samples, we subtract the parameters, and we divide by this standard deviation. Again, as with all t distributions, there's a degree of freedom argument involved here. When we're using technology, it will deal with the degrees of freedom differently. But if you are using a conservative approach, you are going to choose whichever degree of freedom is smaller when we do the subtraction from each sample size. So again, you notice that they're saying n1 minus 1 and n2 minus 1. Whichever one is smaller will be the degree of freedom that you use in your future calculations. So once we've understood what we do as far as calculations are concerned, we have these particular conditions. Again, the first two we've talked about a bunch. Much like proportions, you have to verify that the 10% condition is satisfied for both populations, not just the one. When it comes to the large sample requirement, we know that if the populations are normal, well then we can say that the sampling distribution is normal. Or if the sample size is large enough, we can apply the CLT in stating that the sampling distribution will also be normal. The tricky part, of course, is if we have a sample size less than 30, in which case we will have to use graphical means to verify the use of a normal distribution for approximation. Again, because we are checking both distributions, if either of them or both don't satisfy the sample size requirement, then you're going to have to create graphs to verify this. So if we're going to create a confidence interval, again, we've already talked about how to calculate the standard deviation. We've already talked about how to calculate a t-score. So when we're finding the confidence interval involving means, then this will now be our general equation when we have two means. Again, the degrees of freedom are stated very clearly. This is hopefully getting repetitive in how we apply it. There is a general equation that they give you on the equation sheet. You just have to know what is your statistic and how you apply it. When we're talking about a significance test, we go through the same process as before. Remember that when we're dealing with two means from two different populations, then we're going to go ahead and say that our null hypothesis is that the difference is equal to 0. Remember that when you do this, the direction of subtraction will matter to the next part, which is the alternate hypothesis of whether it's going to be greater than, less than, or not equal to. So keep in mind that it really doesn't matter. Hopefully you follow the question and perhaps make your own initial judgment so that you end up with a positive value or whatever the case may be. But if you don't, so long as you follow the clear steps in a significance test, you should end up with the appropriate p-value to make the appropriate inference at the end. So to do this test then, we take our test statistic, and to find the p-value now we're going to apply this test statistic to the t-distribution with the appropriate degrees of freedom. Again, if you're going to do things by hand, then use your conservative degrees of freedom. If you're going to do things using technology, use it all the way. Just make sure that you are writing out the inputs appropriately and not using calculator speak. So to summarize this significance test, again, with state, plan, do, conclude, the state would be the hypotheses and context of the problem. The plan would be following the conditions. The do would be actually doing the calculations of the test statistic and the p-value. And the conclude would be to actually conclude based upon our understanding of the p-value and its relationship to whatever significance level we're looking for, writing it in context of the problem. At the bottom, you can see that if we're dealing with a one-sided test, that's a pretty straightforward calculation. If we're dealing with a two-sided test, just remember that you have to find the area of both tail ends and then add them up. That will be a little tricky if you're using a table because the table only gives you one side. Just make sure that you double the value. When we're using a two-sample t-test, it's important that we know a couple things. The first thing to know is that we absolutely don't pool in AP statistics. There will be a pooling for a t procedure somewhere down the road, but it's well beyond the scope of this course. So if you are to pool, it is for proportions only. Absolutely don't use it for means. We are totally fine to use this particular procedure when we're dealing with means in a randomized experiment, but watch out for the paired data. Remember that paired data is sampling from the same population versus this two-sample scenario where the samples are coming from different populations. You have to remember that without randomization, there's no chance that we're going to be able to make any sort of statement that would be meaningful to the population as a whole. So like I said, this is a quick lesson because it's all piggybacking on the previous lesson. But that being said, hopefully by now, with our work in the last 3 units of this course, that we have a great sense of how all of those foundational lessons apply to the significance testing and confidence interval creations of now. Thanks a lot, everybody, and you have a great day.